All right, chapter 3. Let's go for it here. So the first hour we're going to do 3.1. And we got to the point of polynomial and rational functions here. Polynomials, we will know what those are in just a bit here. Rational functions are fractions. And again, repeat of Math 63, except for the fact is we're going to add a lot more graphing into it. So we're going to see the graphing sort of connection to the stuff that you guys have been doing in Math 63 here. Anyways, graph a quadratic function, and then solve problems here. Let's go for it here. So first of all, I think you guys know this here. Quadratic function is in this form right here. It's a trinomial, usually. So f of x is equal to ax squared plus bx plus c. And again, I'm going to reference page numbers here. A little easier. And we're going to go kind of quickly here because we have going to spend an extra hour to go over homework here. All right, and if you guys tell me what the page number is, if I don't know it, that'll be great. So page 292 is where we're at. Definition of a function here. So normally, this is the way we know quadratic functions to be. The only problem is this is not a good way to graph them. So we're going to have two different forms. We're going to have this called the trinomial form, and we're going to have another form, sort of more like a graphing form. And we're going to switch between the two here. But first of all, we want to know, and there it is, this is called the standard form, sometimes called the graphing form. Why do we put it into this? So much easier to graph. Because once we have it in this here, we know the vertex. Remember, the vertex is either the lowest point on the graph like this, or it could be the highest point like this. So both of those are h comma k. All right, this is page 293 now. All right, let's go for it here. So first thing we should notice you have x minus h inside the formula. Then you have a plus k. But when the vertex comes along, it's just h and k. So technically what we do is we take the opposite of the h, and then we take whatever k is. That's the vertex. And the vertex is either a minimum point or a maximum point. And I think we know this from even last time here. What determines a graph going up? That means a is greater than 0. Good there. With a being greater than 0, you know the vertex has to be a minimum point because it goes up on both sides. If a is less than 0, the vertex then becomes a maximum point. And then we know what to do from there. Okay, and then also the minimum value is the k value, the maximum value is the k value. In both instances, it's the y value that makes that. All right, let's keep on going here. So first example here, again, this is from your textbook here. We'll at least want to walk through an example, and then we'll do it together here. So find the standard form of the equation. Don't need to write this down. Just kind of think with me here. We'll do the next one anyways. Write the standard form of the equation of a function that has a vertex of -3, 4, then also passes through the point -4, 7. The question is it a maximum or a minimum? So notice it's this equation right here. It's the standard form that we're going to plug into. The reason why we do it is because h and k is given. If you know the vertex, we're going to plug that in directly. So when you plug in the -3, it becomes a +3. We plug in the +4, it becomes +4. The only thing you don't know from this form is the a value. So for parabolas, you need to know the vertex. Then you need to know one extra point somewhere along the graph. Because what we do is we plug in -4 for the x, 7 for the y, and as we do some algebra, we come up with what the a value is. Hence, then we can write down the formula. There it is. There's my equation to a graph that has that vertex and that point. Real quick here for you guys. Is the vertex, is that a maximum or a minimum point? We'll have to look at our A value. Our A value is positive, right? Because our A value is positive, you know the graph opens up. That means it goes like this. That means the vertex is a minimum point. We good there? If the A was a negative value, then it would be a maximum point. It reaches a certain max, then it comes down. All right, so all yours here with this one. Find the standard form of the quadratic function whose graph has a vertex of 1, -5. Practice problem number 1. Passes through 3, 7. And again, the question is, does f have a maximum or a minimum? So again, give you guys 30 seconds or so. Try it yourself. Hopefully have your textbook open so you can sort of follow along on the example given. And of course, everybody read ahead already, so that's good. Everybody has the vocabulary down. Everybody at least look at some example problems. Some of you guys even tried the homework already before class. That's super cool. Alright, since we're running slightly low on time here, I'm going to just start it already here. So, standard form equation is given like this. Since we know the vertex is 1, -5, I'm going to plug in a 1 for the h. It's a -1 as it comes in here. I'm going to plug in a -5 for the k, so it makes a -5. So notice I got everything I need except for that a value. So that a value comes from the second point that I know. It goes to 3, 7. Therefore, let's plug a 7 for the, oh, there it is. So I know that f of 3 equals 7. Plug in a 3 for the x. Gives you a 7 for the f of x. And solve for a. Alright, hope you guys did already here. So let's see, simplifying 3 minus 1 is 2. 2 squared is a 4. After that, how about adding 5 to both sides, then dividing by 4 gives you a is equal to 3. There, I got it. I got an equation of a quadratic equation. Not bad, that's pretty cool. Remember how in geometry we said 2 lines determine or 2 points determine a line? Well, in this case, if we know the special point along a parabola, the vertex, we only need another point. So we technically can have 2 points determine a parabola as well. Okay, so since it's 3, parentheses x minus 1 squared minus 5, question, is the vertex a minimum or a maximum? It's a minimum. You got it. Since a is equal to 3, a is greater than 0, you know it opens up. Therefore, our vertex is a minimum value. Do some graphing here today. Okay, so let's go backwards. Let's go the other way here. How about if we were given a function, can we graph it? That's what we want to do. The book presents like a whole scale of things how to do the graph stuff here. So it says step 1, graph the parabola, identify a. Step 2, determine if it goes up and down. So we'll do all these here, but in terms of problems here. So example problem here first. Let me go to this one here. Again, this is on your textbook here. It's example 2, given this problem. Let's think with me here for a little bit here. So a is -3. H is -2. Remember, it's the opposite of this. and k is whatever that number is at the end here. So first of all, does it open up or down? A is -3. That means it's going to open down. So we have a parabola that sort of looks like this, somehow, somewhere. Get our vertex. Our vertex is -2, 12. So immediately I know where that guy is. So that's an important point. I just figured that one out real quick. And really from here on out, then the question really is, how wide does it go? Is it really stretchy or is it really steep at this point? Okay, but we do have some other important points we've got to think about. And really it's all the intercepts. Because in calculus, we're interested when it reaches a maximum or a minimum. So if you think about business, you're thinking about maximizing profits or minimizing costs, right? You don't care about anything else at that point. In physics, we care when the missile leaves the ground and where it ends up. So you care about that intercept where h is equal to 0 when it hits the ground. So with most graphs in calculus, maximum or minimum points, and where does it cross the x-intercept, where does it cross the y-intercept. That's really what we're interested in. And usually the curve of the graph. So at this point, yes, we are going to solve for, looks like the x-intercept, and sometimes you may have to do a little bit of algebra. Notice we move stuff across here, we divide through by -3, and then we do square root of both sides. And so there's going to be 2 x-intercepts for this one particularly. We turn around and start doing the y-intercept. So we replace x with 0, and we figure out the y-intercept is. So really, if you think about direction, vertex, intercepts, that's kind of what we're interested in. And then we got it. So there's my vertex. We know it opens down. I got these 2 other points, and I'm good to go. I can make a graph. In fact, no. Sometimes if you want to make a little rough graph, it doesn't matter. We usually just get the y-intercept, the vertex, and we're good to go. But again, most of the time we want to figure out these x-intercepts. Alright, so all yours here. Again, have the book open if you want to look at it as you're doing this process. Alright, so the first one is just direction. So what do you guys say? This guy opens up or down? Let's see, opens. It's open. It's going to open down because a is a negative value. So again, we have things going downward. What's the vertex? Perfect. -1, 3 is the vertex. Again, opposite of my h, opposite of the 1 inside the parentheses, and then the 3. And the vertex, is that a minimum or a maximum? Cool, it's maximum at x equals -1, and the maximum value is 3. We good? But it's a maximum. Okay, how do we know it? Because the a value again. Because it opens down, you know, the highest point is going to be that vertex. It's going to be the top of the mountain. Alright, then can you find for me any y-intercepts? Or actually, find me the y-intercept. Then can you find for me any x-intercepts? Let's you guys try that. It's going to be a little bit more complicated than the example problem. give you guys about 30-second head start, and then I'll start it as well. All right, 30 seconds up. Let's go for it. So the y-intercept, again, all we're going to do is we're going to plug a 0 in for the x value. 0, 0 plus 1 is 1, 1 squared is 1, and that becomes a negative 2 plus 3, which is a 1. X-intercept gets a little bit more difficult. And again, x-intercept if any. Sometimes there could be 2 as the parabola is going down, like on the previous example. Sometimes it could be just 1. The vertex is actually on the x-axis, or it could be 0. So we've got to be thinking about that. Anyways, what we do is we plug in f of x is equal to 0. And we have to solve for x. So at this point, let's see, how about subtract 3 from both sides? Divide by 2 on both sides. Ooh, that's no fun. We have a fraction in our hands here. Alright, still got to do it because we can still finish it up. And then we're going to take square root of both sides here. So square root of this side, square root of this side, again plus or minus, because there's 2 possibilities for that. And you can write it as 1.5. Some students like to write it as 1.5. You can leave it as 3 halves. So plus or minus 3 halves is equal to x plus 1. So that means if I solve for x, I have to subtract 1 from both sides. So how about a negative 1 plus or minus the square root of 3 halves? Alright, some students, what they do is they actually multiply all this out. They'll FOIL this out, multiply through by negative 2, add 3, and then they'll do quadratic formula. If you do that, it's the long way about it, but you'll still get the same answer. Any which way, if you plug in the quadratic formula, you'll still get that answer right there. Alright, so you can write it like this, or you can write it as negative 1 plus or minus square root of 1.5. Okay, and you have to have some kind of sort of idea where that is. So on some of these questions, you may have to use a calculator. Approximate square root of 1.5. So it'd be negative 1 plus the square root of that, negative 1 minus the square root of that, and figure out where it is on the number line. Okay, are we good with this one? Can you take it and graph it then? Alright, let's go for it here. Hope you guys got it here. Let's see. Negative 1, 3 was my vertex. Zero comma 1 was my. Thank you. I'll try to take that off the video, so you guys don't get scared. And then anybody with the calculator figured out where is negative 1 plus square root of 1.5? Probably a little bit above 0, huh? So 1.5, I imagine is kind of be like 1.2 or something, 1.23 or something. .2. Ah, perfect. Okay, cool. So there's my 0.2, and this one is a negative 1 minus 1.2, so it'd be a negative 2.2, so a little bit above there. And again, once we have those points, we're good to go. There's my graph. I got the main points of the graph. And the only thing is, don't make it a V shape. Make sure it's like a U shape, because parabolas don't have corners on them. Okay, now we got a little problem though, because we can graph off the standard form, right? Standard form is easy. Get your vertex, intercepts, you're good to go. But most of the time, our parabola is more like this. Our parabola is in the trinomial form, like this. So if it looks like this, we have to have a little bit different rules for graphing. And really the only main one that changes is the vertex. In Math 63, hopefully you guys figured out how you go from a standard form to trinomial form and what happens there. But the A is still here, no changes there. But there's this B value and the C value that's going to change a little bit here. So first of all, we don't have the H and K value anymore. So what would you do? Again, don't have time to show it to you right now here, but you can take the standard form and try to change it into the trinomial form. And what you get out of it is something looks like this. B, you get H plus B over 2A squared plus 4AC minus B squared over 4A. That's kind of what you get out of it. If you try to solve one into the other. Now why did I show you that is because of this right here. Notice I put this into H and K value. What's my H value? It's this, the opposite of this, right? So H technically here is negative B over 2A. That's what I get for H. If I take, again, trinomial form, change it into standard form. The K gets really more complicated. I don't want to plug that in for K. But an easy way to do this is whatever I get for H, what I'm going to do, I'm going to plug that back into my function and figure out what the Y value is. That's what this says. This says I can figure out my H value this way. Just plug in negative B over 2A. Once I know what this value is, I plug it back into my original function, and I can get my Y value right away. So let's see one in progress, and then let's try one together. Time is going fast here, so let's... Alright, example problem from the textbook. There it is. My A value is 2. My B value is 8. C value is negative 10. So again, this still stays the same. A is a positive value. Since A is positive, the parabola opens up. We good? No changes there. Changes are in step 3. How do you find H and K? So all we're going to do is we're going to plug into this little formula right here. Negative B over 2A. So according to our problem here, B is 8. A is 2, so we're going to plug in those values. 8 and a 2 here. That becomes 4, so negative 8 divided by 4 is a negative 2. That's my H value. Just figured out my vertex. Take that negative 2 value, and what we're going to do is we're going to plug it back into my function itself. And if I do a little bit of work, I get negative 18, and voila, I get my H and K. And of course the question is minimum value or maximum value. It's a minimum value. The reason for it is because, remember, A was equal to a positive 2. Since A is positive, the graph opens up. And if the graph opens up, the vertex is the bottommost point along this graph. And of course, then at that point, then you have to figure out the x-intercepts, y-intercepts, and then you can graph it. One extra thing they start putting into this equation, something called the axis of symmetry. Let's take a look at that before as well. This little dashed blue line right here, axis of symmetry, and what that line really is x is equal to -2, and that -2 comes directly from your vertex right there. Good there? So as you know, that point is the vertical line that makes that at that point is the x coordinate. So we take the x coordinate and we technically just make it into a vertical line. And I like this. Why is it dashed? Because we're not including stuff on that line, right? That line is not part of our answer. Our answer is just this parabola here. All right, so let's try it. Give you guys a head start here. So 3x squared plus 3x minus 6. Can you eventually graph that? And of course, it's going to be more complicated. And the reason how I make it more complicated, h becomes a fraction. Then we've got to deal with fractions here. All right, I'm going to start it here. So vertex. I guess we should even, let's see, this graph is, let's even back up just a little bit. I didn't write it down here. Graph going up or going down? Yeah, it's going up because the a value is positive 3, so we have a graph that goes up. So let's go with the vertex. Vertex is negative b why do I have a negative in there? I don't know why. One second here. Let me check the practice problem here. Sorry. Okay, I messed up with here. Sorry. The practice problem itself doesn't have a positive, it has a negative in here. Let me do this. It should have been, sorry, it should have been 3x squared minus 3x minus 6. So as I plug it in, it's a negative of a negative 3, which becomes a positive 3, and at this point you get ourselves 3 on top, 6 on the bottom, gives ourselves a 1/2. And again, that's the h value. To get the k value, we're going to have to plug it back in. So I have to plug in a fraction back into our function. Square it, minus 3 times 1/2, minus 6. Huh? Yeah, what we do is we plug in h into the f function to get k. Because I wrote it wrong. In the practice problem itself, there's a negative here in the problem itself. No, because for the formula for h, it's a negative b over 2a. So it's negative of the negative 3. Okay, no problem. Let's simplify this out. And so we have ourselves, let's see, 1/2 times a half is a fourth, so 3 times a fourth. 3 times 1/2 is a -3/2, minus 6. So multiplying all that together, it makes 3/4 in front, minus 3/2 in the middle, and a minus 6 at the end. Hopefully you have a negative 27 over 4 already, but you'll have to get common denominators. So between 4 and a 2, common denominator is 4. So let's make everything into a denominator of 4. So let's see, that stays the same. First fraction remains a 3. Second fraction, you got to multiply by 2, so 2 times 3 is 6. And this one, it's going to be 6 times 4, or 24. Whew, 3 minus 6 is a negative 3. Negative 3 minus 24 is negative 27 over 4. Alright, again, a little bit tougher than the example problem. I got both of them as fractions here. But I can pinpoint that on a graph, right? Cool. Alright, with that, there's my vertex. I know which direction the graph is going. I got to figure out my x-intercept, y-intercepts, and I'm good to go. Cool. And then, everybody okay with this here? The vertex is the minimum value since the graph is going up, and the value at that minimum point is negative 27/4. Alright, so intercepts. Let's go for it here. X-intercept, we plug in the f of x as equal to 0, and we have to factor and solve if need be. Let's see, I think I can factor out a 3 out of this. 3 leftovers are x squared minus x minus 2. And can I factor this guy? Let's see, negative 2 and a positive 1 maybe? I think that'll do it. So negative 2, positive 1 would be the factored form. All the stuff you learned in Math 63. So that means 3 is equal to 0, or x minus 2 is equal to 0, or x plus 1 equals to 0, and got to solve each of those. Obviously this doesn't make sense, right? 3 can't equal to 0, so that gets crossed out. But I have two answers here, two x-intercepts, 2 and negative 1. Alright, the y-intercept here actually becomes really easy. The y-intercept, you plug a 0 in for the x values and see what happens here. And notice anything that has an x next to it is going to become a 0. So f of 0 technically is negative 6. Or can we just say it's the c value in a trinomial? A values goes to 0, the b value goes to 0 because you're multiplying by 0. C value is the only thing that's left. So y-intercepts are pretty easy in trinomial form to get. Okay, and one more thing the book talks about is getting that axis of symmetry. And so what we do is we go back to our here, take our vertex, and we take this 1/2, the x coordinate right here, take the x coordinate, and we say that's going to be the symmetry. Symmetry is about the line x is equal to 1/2. So one half, and then we go down -6 and 3/4. Is that right? I can't really make a nice dot there, so I'll do it right there. X-intercepts, y-intercepts, and we have ourselves a graph. Alright, for the sake of time here, what we'll do is we'll do each of the practice problems here. You guys have the example problems to sort of refer back to. I think between those two, I think we'll be okay as far as seeing it. So practice problem here. So now that we know how to graph these things very quickly, at least get important points, can we start solving equations? Can we start solving inequalities? So remember how we used to do this before? We used to do it by test points. We used to get it, figure out whether it equals 0. You line up all the different intervals. You pick a test point. Now, since we know how to graph these, can you quickly graph 3x squared minus 6x minus 1? Okay, it's in trinomial form. So I know because of that, my h is going to be something. So again, the vertex, you know direction already because of the 3. So the vertex is probably the most important point here. So h is equal to negative b over 2a, which is negative of a negative 6. 3 times 2. Let's see, 6 over 6, or just a 1. Cool. Our h value is 1. Can you plug 1 back into the function itself? And that will give me the vertex. Plugging a 1 back in. Again, should be pretty easy to plug in here. So f of 1 is 3 times 1 squared minus 6 times 1 minus 1. So 3 minus 6 minus 1 should give you minus 4. Check just to make sure I did it correctly. I think I did, yeah. So 6 minus 3 is a negative 3. Negative 3 minus 1 is a negative 4. Cool. So 1, negative 4 is my vertex. Got that one. The y-intercept, easiest thing in the world. What is the y-intercept? It's the c value right at the end here. Got myself the negative 1. Easy to get. The x-intercept is the only one that sort of takes the time here. So we plug x equals 0, and at this point, yes, we must factor or use the quadratic formula. At this point, 3, 3, and 1, 1. I tried factoring a little bit here, not going to happen. So I'm going to use the quadratic formula. So negative b plus or minus the square root of b squared, so that's 36, minus 4 times a times c, whatever that's going to give me. That's 12, right? Yeah, 12. So 36 plus 12, technically, over 2a. If we do that, that becomes a 6 plus or minus the square root of 48 over 6. All right, going some more here. Let's see, 48, perfect square with inside 48. I heard it, yep, 16, something like that, right? So 6 plus or minus. 48 is 6 times 8, but also you can say 16 times 3. All right, where 16 is the perfect square, so that comes out as 4 root 3 over 6. And can I reduce? Maybe, sometimes. Yeah, remember whenever we have quadratic formulas here, if I can reduce this number in front, the number in front of the square root, and the denominator at the same time, that means I can reduce this whole thing. So a number goes in 6, 4, and 6. 2 will do it, yep. 6 divided by 2 is a 3, plus or minus. 4 divided by 2 is a 2. Root 3 over 6 divided by 2 is a 3. Okay, those are my square roots. Again, have to use a calculator here. Can you take a calculator and approximate those square roots? At least so we can have a graph. Alright, but the whole point of these graphing things is not so much for you to write down every single step, have it on there. Really, the whole point is, can you actually maybe possibly graph it without writing anything down? That's sort of the question. And except for the x-intercept, and maybe a fraction for the h, you should be able to almost do this without having to write maybe anything down at all. Just like we do with lines. Remember, if you have it as y equals mx plus b, you look at the equation, you graph it, you're done. So it's sort of the same thing here. You want to be able to look at the equation, graph it, be done. Alright, if that's the case, 1, negative 4 is the vertex. Is this okay for the x-intercept? It's in between 0 and negative 1. The other one should be a little bit above 2. And the y-intercept is negative 1. Again, graphing this all together. There's my graph. And the question is, when is this graph below? Let's see, what's my question again? We've got to solve this inequality. When is this graph equal to or below 0? That's what I want to know. Well, let's see, equal to or below 0, isn't this right here, from this point to this point? It's this little interval right there. Again, what is that? And now are we including the 0? Yeah, we are, because it's less than or equal to 0. So at this point, the interval that this is made is from, again, there's my equation. That's what I'm trying to, inequality, that's what I'm trying to solve. But the solution is this one right here, which was the x-intercept, which is 3 plus, or sorry, minus 2 root 3 over 3. And the other x-intercept is 3 plus 2 root 3 over 3. And again, this little interval between this number and this number, that's when the graph goes below 0. All right, good there. Let's go just a little bit more abstract. This is practice problem number 5. So here it is. I have just an abstract concept. It's ax squared plus bx plus c. So what I want to know out of this is just the signs for a, b, and c. So is a positive or negative? Is b positive or negative? Is c positive or negative? And can I figure that out based upon the description or the graph given below? And again, this is a sort of backing up, taking a very abstract view of this here. So real quick here, all yours. A is positive or negative? Perfect. A is negative. A is less than 0 because it's going down. Next, B positive or negative? Well, that one takes a little bit of time to figure it out here. And that's probably the one that needs to take the most amount of time to figure out. So remember, we do have a formula that connects B and A and H at the same time. And we also understand, everybody okay with this here? Is H less than 0? Right, it's left of the y-axis, right? So the x coordinate here is negative. So in that case, this is my formula. But I know a few little things here. I know since h is negative, technically I have a negative h here. And because a is negative, technically I have a negative value here. So if I were to multiply negative 2a both sides, I get negative h times a negative 2a. Negative times a negative. Positive, right? But then if I divide through by negative 1 over here, I'm still going to get a negative 2AH. And therefore B is also a negative. That's a tough one. If you got that one, that was pretty good. All right, C, positive or negative? It's positive, yeah. It is because C, remember, controls the the y-intercept. Since the y-intercept is above the x-coordinate, you know that C is greater than 0. Again, if you got that, you did good. Because that was no numbers, just a lot of thinking through the process. Okay, and the rest are really application questions here. I got number 6 and number 7. For practice problem number 6, we actually have to go through the example because it focuses on the example to do it here. So this is from your textbook, page 298, if you want to follow along. Page 298, and this is it right here. This is a generalized formula for any object thrown up into the air and then coming back down. There it is. It's 1/2, and this guy is the constant of acceleration of gravity right here. It's g sub e. T squared is in terms of time. V, we call this v naught. It's the initial velocity that you're throwing the ball up, and h naught, sometimes s naught. This is initial position, how high you are when you throw the ball up in the air already. We'll get back to this equation, but real quick here. So find the height of the ball as a function of t, and then how long will it take the ball to reach the highest point? Again, going to go through this here. It's inside your textbook here. First of all, let's make up the equation. First of all, I got to put this right here, this little gravity constant. And that's going to be, anybody remember this from physics and high school physics? It's 32 feet per second squared. That's how fast gravity pulls you down, so let's put that into this equation. If I do that, 32 times a negative 1/2 gives me a negative 16 t squared. See, if you throw the ball upward from a cliff 50 feet high. So if you are standing already on a cliff 50 feet high, that means this guy here, the H sub naught is 50. And the maximum height that it reaches is 99 feet. So we got a little issue here. We know the maximum height. We know where it's released from. The thing we don't know is how fast did we release it. So that's this guy part right here. So if it reached a maximum height of 99 feet, what does that mean? Hey, that little formula, isn't it? H is equal to negative b over 2a. So if that's the case, we can plug in this right here, except in this terms it's going to be in terms of t. It is negative v naught over 2 times a. And if we do that, we actually have a little problem here because its t is connected to v naught of 32. But we know it reaches a maximum height of 99 feet. So all we do is we plug this guy in for all the t values. Again, a little bit of work here. It's an application question. And eventually, after a little bit of work, we get ourselves an answer for v naught is 56. And we finally built our equation for this type of problem. Again, launching a missile. Usually we can determine how high it went up in the air, the maximum amount, and then we can determine where it landed. So if you want a parabola or a quadratic function that determines that, that's all the points you get. And so from there, can you build the graph? That's kind of what we did over here. So initial velocity of 56 feet per second. When it launched, once you get that, there we go. Then we can plug in the parabola formula as 56 now. As you plug in, it takes 1.75 seconds to reach a maximum height. From then on out, goes down. Whew, I don't know if we'll have time to do. Oh, let's try it. All right. Repeat example 6. Assuming that the height of the cliff was 100 feet, so twice as high now, and the ball reached a maximum height of 244 feet above the ground. All right, let's go for it. So h of t, negative 1/2 get squared plus v naught of t plus h naught. Okay, what do we know? Gravitational constant we know. Plug in negative 32 right into here, or 32 right into here. That's going to be negative 16. It is, let's see, we shot it up from 100 feet already standing on the cliff, so that means this guy has to be 100. All right, and again, plugging in negative b over 2a, the vertex formula. And again, the b value is v naught over 2 times a, which is negative 16. At that point, you get yourself a negative v naught over negative 32, or, hey, that's the same thing that we got earlier. And again, we've got to plug that one back into original function, knowing that the maximum height is 244 feet. Almost done. Just for the sake of time here, let me run through it here, and if you want to see it again, you have the sort of the YouTube video to look at real quick here, just to see if you can see it. So remember, it reached a maximum height of 244 feet. We plug that in and we plug in the t value. So it's v0 over 32. And as we do this here, simplifying here, let's see, we're going to square this guy. So this is negative 16 over v0 squared over 32 times 32, or 1024. Again, a v0 squared because they multiply together with a 32 and 100 over here. And then we're going to see if we can simplify that right there. So 16 into 1024. When we do that, yeah, it goes 64 times. Cool, we got that one here. So plus v0 over 32 plus the 100. Again, just simplifying some more here. Got to have a common denominator of 64. Or maybe we can do is we can just multiply through by 64. That'll probably be even easier. So I'm going to rewrite it so it doesn't get too messy. But let's multiply both top and bottom. So both the right and the left hand side. By 64. Before we do that, maybe we'll just move the 100 over. That's probably the easiest. Just so we don't have to humongously big numbers here. Moving the 100 over, and let's multiply 64 on this side, 64 on this side. Again, huge number here, 9,216. Alright, this is both V0 here. There's a V0 over here, there's a V0 over here, so adding these guys together, negative of those guys, and 2 of those makes 1 of those. And again, I'm going to go a little quickly here because of the time here. There's that. Adding those guys together gives you just 1 of those. And in order to get this here, we've got to do square roots of both sides. And I'm not putting a plus or minus on there. For the simple reason is because velocity can't be negative because we're throwing it up into the air, not down. We'll have to choose which one we want. And it turns out to be exactly a nice 96. So finally there it is. I've given a formula specifically for this type of problem. There it is. Negative 16t squared plus 96t plus 100. Okay, almost done. Not quite with this problem here, because that's the formula. Now the question is, how long does it take to get up to the vertex, or how long does it take to get to the maximum point? So if I have stickman on a cliff, 100 feet high, the question is, when do you get to 244 feet? Well, remember this is sort of concave down, right? It goes down. So isn't this point called the vertex right here then? So technically we just need to figure out the vertex. We have the formula already. And technically we just need to figure out, let's see, we're asking how long will it get there. So at this point I'm only asking for the x coordinate of my vertex. That's kind of important to know. So in this case, since my formula is given like this, and I want to know when it gets up to the maximum height, I only need to solve for this guy. If it's asked me what was the maximum height, then I will have to plug this guy in back into the equation and they'll tell me what the maximum height is. But in this case I don't care about the maximum height, I just care about the time it takes to get there here. So negative b over 2a, negative 96 over negative 32, and we get ourselves, it'll take 3 seconds to get to a maximum height. Next one is the one that you probably find most likely in calculus here. We've got one more problem to do here. Let's go to last problem here. Finding a maximized area. So a children's center receives a donation for 1,000 feet of fence to enclose a rectangular playground. That's kind of cool. So what is the maximum area that can be enclosed? And then what are the dimensions of that playground? And this one you'll see very often. You set up one problem, and it's actually related to another problem. So let's see how that works here. So I got a rectangular playground. And if I have 1,000 feet of fence, doesn't that really mean perimeter? I got 1,000 feet, which is the fence around, which is perimeter. So then I say to myself, okay, what's the perimeter formula? Or I can also define the variables here. So it looks like x would be my length, y would be my width of this playground. And from geometry, we know that p is equal to 2l plus 2w. So let's plug in what we know. P is 1,000. I can plug that in. The length is x, and the width is y. But that's not what I'm trying to maximize. I'm not trying to maximize perimeter. I'm actually trying to maximize the area. So this is what I used to do in calculus here. So the one I want to maximize or minimize, I'd write A for area, and then I'll set up a little formula. So again, we eventually want to maximize this right here. But we got technically, this is called a constraint. You can only have so much fencing available to you. So notice over here, our problem is that you have two different variables. You got an x and a y. Can't use that until we've solved for one of those. So we have strictly one variable in terms of another variable. That's it. So I want area in terms of one of these variables, not both. So what we use this right here, we use this to substitute. So let's do this here. Let's solve this one. It doesn't matter, x or y, whichever one you want to solve. Let's solve for x. So I'll subtract 2y from both sides. Gives me 1,000, subtract 2y. Divided by 2 gives me 500 minus y. Good there? So now I have x in terms of y. Then that means I can come over here and I can substitute this and put a x in terms of y now. Hey, that's kind of cool. Now I have area in terms of the y coordinate, or actually the width, not the y coordinate, just the width. So notice over here, this is a, if you think about x's and y's here, this is a linear function. This technically means x and y. Kind of careful when you get over here. This is, the y is technically the x coordinate, we good? And the area are really your y coordinates. Does that make sense? These are your input values, area is your output value. So you're moving on to a different graph here. But let's go. Distribute the y to each of those. And I don't like the way it looks like that, so I'm going to put the negative y squared in front and put the 500y in the back. So okay, so we got ourselves an area formula. Kind of looks like this if we're to graph it. Kind of goes like this. Like that. Everybody agreed? If it's 0, if y is equal to 0, there's that one. Y is somehow 0 again here. But here's what I want. I want this. So isn't that a vertex? Question. Do I want the x coordinate or the y coordinate of the vertex? Depends. Let's see. If I'm talking about what is the maximized area enclosed, that means I want the y coordinate, right? I want the area itself of this graph. I want this one right here. I want the area. What are the dimensions? Once I enter dimensions, now I want the x coordinate. I want the input values for those. So let's see what we got here. So area okay with A is -1, B is 500. And so if I want to figure what the H is from H and K, I'm going to plug in this. And again, what is that H value? That's the X coordinate, but my input value, or my input value for this vertex, my input value is Y. So if I have that to be H, technically I'm going to find the K value. Or, you know what? Maybe it's easier to think about this as, can we change this into a Y instead of an H? Let's change it into a Y, because that'll probably make more sense to you guys. That's the Y value right here. And then plugging it back in, since I have the Y value, I'm going to plug back in over here for the X value. So plugging in for the X value. Alright, so what do we figure out this here? The length and width are both going to be 250 feet. So what maximizes the area is a perfect square, which kind of makes sense. 250 here, 250 here, 250 here, and 250 on that side, right?
That was a rectangle.
Ah, cool. So real quick here, is a square a rectangle? Yes. Square is a rectangle. So if I say, give me a rectangle with these dimensions, you could technically still have a square. Alright, this happens. It's kind of interesting on the homework. I think you guys have a different example where you're bordering a river. When you border a river, things change, because it's no longer 1000 is equal to 2x plus 2y, because you don't have two widths and two lengths. You just have one length and two widths. And because of that, these will change. Alright, but we also want to know, we just figured out the dimensions. We also want to know what is the maximized area. To get the maximized area, we still have to plug into this function right here. We're going to have to plug in the y value of 250 and do it on a calculator if you need to here, and eventually you wind up, you have, that's how much square feet you have in the yard with that much fencing. And now of course the cool question is, what playground structure can you put in? What